Hey everybody, in this video I decided I'd challenge myself with trying to figure out how to hit this little action figure guy with this steel ball bearing projectile by launching it from this projectile launcher. You can see this launcher actually has a spring inside that you could pull back to 3 different positions. Low, medium, and high range. So the further you pull back the spring, the faster it's going to shoot. So naturally I'm shooting at the maximum velocity. You stick the ball bearing in there, shoop, and then pull the trigger here, click, and it fires the projectile. You can do it at different angles. You can see that there's got this string with the weight there and this protractor. So you can actually set it up at different angles. You can shoot it just horizontally like we did launching the Hot Wheels cars off the end of the table, or I can change it to a certain angle. Since we've been looking at surface-to-surface type projectiles, things that are launched at an angle, and we'll also be looking at other projectiles launched at angles next week, I thought that's what the challenge would be. I picked a 30-degree angle to launch this thing from, and the challenge is to figure out how far away I need to place this guy at the same height as the launcher so that he gets hit in the head. We know in order to figure out how far away, or the delta x, for instance, of this projectile that's going to travel, we have to know some information about the projectile itself, like how fast it's traveling. Specifically, how fast is it traveling in the horizontal direction, even though it is traveling in an arc. We need to know how fast its Vx is, which is how fast it's going to be launched from the projectile launcher, but only the horizontal component of that velocity. We also need to know how long it's going to spend in the air. So not only do we need to do some math, we have to figure out a way to actually find how fast it's being launched from the projectile launcher, because I have no idea. So I decided to do that the same exact way y'all did it for the Hot Wheels cars. How fast are they flying off the edge of the table? Well, that's a horizontal launch, so I figured I'd just position the launcher at 0 degrees, launch it horizontally a few times, and see where it landed. I'd work backwards to figure out how fast it was being launched, and that was going to be my initial velocity for when we launch it at an angle. After a few trials of launching this guy horizontally, I could work backwards and figure out how fast it was leaving the chamber of the projectile launcher. I knew that would be our initial velocity. And then it was time to do some math. With our math all figured out, which I decided I'd put at the end of the video, I'm just going to show you the outline first. We're ready to try and actually see if we can hit this thing on the very first try. So I set the launcher back up at 30-degree angle. I knew that the distance horizontally, or the delta x it should travel if it lands back at the same height it was launched from, should be about 2 meters and 31 centimeters, just about. So I had my boxes set up over there so I could make sure that our action figure guy was situated at the same height from which the projectile launcher was launching the projectile. The only thing left to do was set our launcher back up to 30 degrees. Oh! First try, not bad. You have to see that in slow motion. Nice. Not too bad for first try. So, what we're going to look at is all the math that went around in figuring out how fast our projectile launcher was launching the ball bearing. We did that by launching it horizontally. I'll show you the work for that. Then I set it back up at an angle, and we used our kinematic equations for projectile launches, specifically for a surface-to-surface launch, where our launch height is the same as our ending height, to figure out how long it spent in the air, what was the total time it would be in the air. And with that information combined with how fast it was being launched and its speed in the x direction, or horizontal velocity vx, we're able to figure out delta x, how far it should travel. As you saw, I had to use my blue boxes there to keep my action figure at the same height as the projectile launcher, because this is a delta y equals 0, surface-to-surface type of launch. With that set up, we were successful. All right, hey everybody. So now we're over here doing our math stuff, trying to do the prediction for how far away I need to have this stack of blue boxes that's got my action hero here, who's taking one for the team for us, little physics mascot. He probably needs a name. Anyway, we want to figure out what is the delta x, how far away should that guy be positioned so that he gets struck by the projectile, which is being launched over here on the left by that projectile launcher. Now it's launching a steel ball bearing at a higher speed than most of the things that we got in the classroom, so like faster than the Nerf dart, faster than the balls are rolling off the table when we do that lab. So just to kind of map out what's going on. Okay, so I have a picture here just taken of the room of the basic setup of what we're trying to solve. I got a projectile launcher over there on the left and an orange arrow showing the initial velocity of our projectile and what angle it's being launched at. The angle that I've chosen to use, because I had to pick something, is 30 degrees. So it's a relatively low angle. We call that angle theta, generically. But we know, because I've set it up, it's going to be an angle of 30 degrees. Right now, we don't know what the initial velocity is of this launcher. So we're going to have to do something to figure out what the velocity is. How quickly is this projectile being launched from this projectile launcher? And the main thing we want to figure out is this red delta x across the bottom. How far away do we need to position this action figure so it gets struck by the projectile? Notice that the initial and final vertical positions, so like right here, that's going to be what we call y initial, the initial position. That's at the same height. It's just over a meter. You can see my meter stick over here on the left is the same height as over here, what we would call the y final, the final position. So that makes this a STS, surface-to-surface type projectile launch, where the object is landing, projectile is landing at the same height it was launched from. All right, this will be an excellent approach for solving the assessment question for this week for surface-to-surface launch projectiles as well. So I'm going to say this is an STS type launch, or STS type projectile. Things we want to get down in our T-chart. What do we always know? We always know acceleration in the x direction is 0. We got free fall in the vertical direction, so I know acceleration in the y direction is little g. And as soon as I think about little g, I'm like, okay, that points downwards. Gravity points downwards. So as soon as I see little g, that makes me think, hold up, I need to think about what's going to be my positive and negative direction. In this case, I'm deciding to call down the negative direction and up the positive direction. I'm going to stick with the convention here of using up, positive, down, negative, because my projectile travels in the upwards direction and has positive vertical velocities to start, and then during the second half of its flight it's coming downwards, so it's going to have negative velocities. Since I have both to deal with, I'm going to call down negative and up positive. It's up to you. Remember, you can choose to make to flip them around if you want. You just got to keep track of them. For the x direction, I'm going to call to the right positive and to the left negative. In the x or horizontal direction, the projectile is only going to be ever moving to the right in the horizontal dimension, so I might as well make to the right positive. So g now is going to be a minus 9.8. This is happening in reality, so I'm going to use 9.8 meters per second squared, but you could just, in the problem, use 10, and we want to call it negative here because little g, gravitational acceleration, points down, and I'm calling that the negative direction. Important thing for our surface-to-surface projectiles. See where I've indicated y initial initial y position, and y final y position. It's at the same height. That's characteristic of the STS surface-to-surface type launch, which means my delta y is 0. That's something I always know is true for surface-to-surface type launches. So there's delta y is 0 meters. Easy peasy. Now the rest of the stuff we might indicate in here would be, still on the vertical side, the initial velocity in the y direction, the final velocity in the y direction. There are a couple times you could think about. I could talk about the time it takes to reach the maximum height, usually defined with a capital H. That might be something useful for me to find out. It's one way to approach solving the problem, because this is a perfectly symmetrical parabola here. And so whatever you find out about the first half of the parabola, the first half of the flight time, it's symmetrical on the other side, because this maximum height here that we're going to call capital H, that's halfway through its flight, maximum height. Okay, so I could talk about the time it takes to get to max height. So let's say time to max height. We could call that, let's use slightly thicker ink here, we could call that T sub capital H, and that would be the time it takes the object to get right here. And a very important piece of vertical information we know is that at max height, just like with the Nerf gun launcher very first lab we did, at the maximum height in the vertical direction and vertical motion speak, at the maximum height of an object's trajectory, its velocity in the y direction is 0. So I can say Vy, velocity in the y direction at the maximum height is 0, because that's the point where it's gotten to its highest point and it's about to turn back around and fall back in the downwards direction. So I could talk about the time it takes to get that maximum height. We could call that TH, or T sub H. Or I could talk about the total time, which usually I'll write as T with a subscript, capital T. And we always know the total time is going to be twice the time to the maximum height, because that's the halfway mark. So time to the maximum height, halfway mark, would be where we indicated where the max height is. Time to max height would be the time to get to that point. And then total time would be the time to get all the way over there. That would be T sub T, we'll call it total time. It would be the time to get all the way across. Twice the time to go halfway. So I could indicate two different times there and use a subscript to keep them sorted out. Let's see, what else? So I have, in the x direction, we can come back to the y. In the x direction, I have a delta x that is unknown. That's what I really want to find out. How far away do I have to place this object? And then we have velocity in the x direction that's constant. So I don't need VI or VF. And then I have the same time to the halfway mark and time total. I could list here as, I don't know them, but I could figure them out. Okay, and we're looking pretty good. So let's say the one thing that we always got to do once we start to get our getting underway with our surface-to-surface projectiles is we need to figure out the horizontal and vertical components of our velocity here. We don't know what that orange velocity is, so I've got this vertical component, as we discussed, is the hypotenuse of this triangle, VI. Let's write it up here. VI. And it is opposite of the gold 30-degree angle there. So VI in the y direction, that's what this green line represents, is going to be equal to the hypotenuse VI times the sine of 30 degrees. Similarly, as we discussed, this VI in the x direction is adjacent to that angle. So I'm going to have my hypotenuse, the total velocity VI, times the cosine of, let's call it theta for now. I won't put any numbers in. So I'm mapping out all my stuff. Look at that, directly on the background of the classroom where this thing is happening. Okay, so I can just write those anytime I have a projectile or even a force or anything like that, an angle. I can call my velocity in the x direction here is going to be VI cosine of the angle. And vertically, I'm going to have for the initial velocity vi times the sine of the angle. And something we notice about the from the symmetrical nature of this surface-to-surface type launch, whatever this initial velocity in the y direction is, because we have a symmetrical feature, the final velocity in the y direction way over here, this v final in the y direction is going to be the same number as the initial velocity in the y direction, but negative because it's going to be pointing downwards, so opposite direction. So that's always something I can put in. This is going to be the opposite direction of the initial velocity, but same magnitude, same amount. So that would be minus vi sine theta. Okay, so I've listed out a lot of stuff that I know. I want to predict what the range is, how far away I got to put this our little action hero, delta x. So like we even did with our horizontally launched projectiles, I can look at my second kinematic equation, vxt plus 1/2 xt squared. But we know our acceleration in the x direction for all projectiles is 0, so that goes away. And so delta x, what we want to find out is velocity in the x times
Teachers
time.
and students, at this time, if you're on the 3rd floor and you need bus information, please report to Mr. Hunter's office on the 2nd floor near the library. Thank you.
We know from our table up here, velocity in the x, we've got to be careful, that's vi cosine theta. So I'm going to substitute that in. I don't know what the initial velocity is, but I do know velocity in the x direction will be vi, the initial velocity, times the cosine of that angle. And then if I multiply that by the time, I should get the range. So this is what I need in order to predict how far away I should put that whatever figurine or mascot. So I need to figure out vi. I've chosen my angle arbitrarily to just be 30 degrees because I had to pick something. And then the time, we also need to find that. So what is the time that's going to spend in the air? What is this launch velocity? Okay, so for the launch velocity, how fast it's shooting, I actually had to find a way to measure that. So I did the same thing y'all did with the in-class lab, or if you watched the video for the lab of having the Hot Wheels car fly off the edge of the table, or if you look at the practice problems from last week in our assessment question, having the ball roll off the table. I did the same thing there. I launched our projectile launcher with the steel ball bearing horizontally, looked at a few trials of how far away from the edge of the tabletop it landed. So here's the first one. I just shot it horizontally. And so here's its first displacement, delta x, away from the table when launched horizontally. The second one, you can just see this blur. So I tried to go frame by frame and figure out where it was because it was going pretty fast. There's the second one, and then here's our third value. And so the average delta x for those three trials was 2.3083. I hang on to an extra digit there. So there's the average delta x when this thing is launched horizontally. And I'm doing this to figure out what the launch velocity is, just like you did in your lab with the Hot Wheels car. Okay, so with that Hot Wheels car lab, you used that same kinematic equation, delta x equals velocity in the x times time. And we were looking for the velocity, just like I'm doing here, so I know I need delta x divided by time is velocity in the x direction. And in this attempt here to determine the true launch speed of my new projectile launcher, I'm just aiming it horizontally like that. I needed to know my height of the tabletop or countertop that I was using, and I also needed to know my range delta x, how far it traveled, just like you did for the lab. And with that information I could get the time, and then with these pieces of information I could get the velocity. So that's exactly what I did for this new projectile launcher that's launching the steel ball bearing. So when we go to find the time over here, Remember, we used our kinematic equation, same second kinematic equation, initial velocity in the y times time plus 1/2 ay t squared. With our horizontally launched projectile, as this example is, call down the positive direction is a nice easy way to do it, since it's only ever moving in the downward direction in the vertical sense. So delta y is equal to 1/2 acceleration is little g t squared. And what we found when we do those problems, or we did that lab, is that the time to fall is twice the height it falls divided by little g. Now this was in reality, so I'm trying to figure out the actual launch velocity. So the time that I found was just based on that height, which I had it set up at exactly 1 meter above the floor. Little g was 9.8, and so we have 2 over 9.8 square root of that guy gets us our time to the floor, which should be just about above 0.4 seconds. So it's 0.451 seconds. Just like we were doing with our horizontally launched projectile problems and lab with the Hot Wheels car. So I had my displacement that was measured using my review of the video and slow motion capture to see where that steel ball was landing, and just got an average for it, just like you did with your Hot Wheels car. And then I just calculated the amount of time it spent in the air based on its height, and knowing that the acceleration due to gravity is what is causing it to speed up from rest in the vertical direction. And then we've got a velocity for how fast this new projectile launcher is launching stuff, and that was 5.109 meters per second. Okay, so this is for the horizontal launch. The horizontal launch. So now I'm using that information to say, okay, that's how quickly the steel ball bearing projectile is being launched from that that new type of projectile launcher. This guy right here, this guy is going to launch anything at an initial velocity of 5.109 meters per second. 5.109 meters per second. So you see, I set it up as a horizontally launched projectile first to get the range and the height above the ground, to work backwards and figure out how fast this thing is launching stuff. And then using that information, oh, now I have the initial velocity, how fast it launches a projectile. Now I'm going to change it and turn it into a angled launch. So now my initial velocity that I didn't know before, I used my understanding of horizontally launched stuff to get that 5.109 meters per second. That's how fast it's being shot. So now I can come figure out my other stuff, like my velocity in the x direction. So I've got my initial velocity in orange, 5.109 meters per second, multiplied by the cosine of 30 degrees. I'm going to get a value for that. And then that'll be one of my known pieces of information. And then over here for my VIY, my green value, I can figure that out now because I know my angle and now I know my launch speed. So VIY, initial velocity in the y direction, is that 5.109 meters per second times the sine 30 degrees is our launch angle. 0.425. So Vx is 4.425 meters per second. Remember, this is just the portion of the launch velocity in the x direction being represented by this red arrow that's forming part of this right-angled triangle. That's what we do when we have a vector, like this orange velocity vector, and we need to break it into a horizontal and vertical pieces. So 4.425 meters per second is the red portion. And then my green portion, I got my hypotenuse, 5.109 meters per second times the sine to get the opposite side. Sine 30 degrees is 1/2. So I got 2.5545. 2.5545 meters per second. That's what I'm keeping for my initial vertical velocity. So I can add these to my t-chart of stuff that I know. 2.5545. Notice how I'm slowly collecting more pieces of information about what's true, what's happening with this projectile, because I want to get to my delta x and predict where I need to put this thing so I can shoot it in the head with the launcher. Velocity in the x direction was vi cosine theta, and we found out that value was, what was it? 4.425. 4.425. Aha! Now we're getting closer. Now we just need to find the total flight time. So I want to be able to do this maneuver here, because we already showed what equation we need. Vi cosine theta, we found out that's going to be 4.425 meters per second. That's our velocity in the x direction. Remember, that's velocity in the x direction. So we have that number. So now I just need the total amount of time that this thing spends in the air. I need total time, and I can figure out where to put this thing so I can hit it. So how am I going to find that out? Go over to the vertical stuff, and maybe I can figure out something I can do to get the amount of time from the vertical direction. Like what was very useful in the previous week's horizontally launched projectile problems in this week's lab, I'm going to check out the second kinematic equation here and see if I can get something out of that. 1/2 a in the y direction times t squared. There we go. I check out what I know and what I don't know. Notice delta y is 0. That's because it's surface to surface. Launch height is the same as landing height. So that's something, if delta y is 0, I immediately know this term is 0. Let's rewrite the equation. VIY, that's VI sine theta. Remember, we also already calculated it. Then I got multiplied by times, or multiplied by t, multiplied by time, plus 1/2, acceleration in the y is just little g, so I'll throw that in there, t squared. Okay, so we've got time that we want to solve for. That's what we're looking for here. We're trying to find out how long does it spend in the air. This is going to be for the whole trip, because if delta y is 0, that means we've gone on the whole trip, beginning to end, same launch height, delta y. If delta y is 0, you're talking about the full symmetrical parabola, the full projectile's trajectory. So I'm going to subtract my first term here, vi sine theta t. So I get it on one side, and I'll have 1/2 times g times t squared on the other side. And notice that I do have a time go away. One time will cancel out if I divide both sides by t. And I'm left with minus vi sine theta equals 1/2 gt. I'm trying to get my t by itself. So let me multiply by 2 and divide by little g. I'm going to have minus 2 vi sine theta divided by little g equals my time t. I got t by itself, and now I'm good to go to substitute in some numbers. You might be worried seeing a minus sign there, and this thing's going to be equal to time. What are we going to get, some minus amount of seconds for something? No, we're not, because we kept track of what's going to be positive and negative. If you do get something minus for time, then you want to make sure you go back and make sure you're using your pluses and minuses correctly. So I've got minus 2 times vi sine theta. That was we have a value for that already. Vi sine theta, see it up here. We kept track of it, 2.5545. So we have minus 2 times 2.5545. That's the vertical component of our starting or launch velocity, divided by, now little g's showing up, we're calling down negative, so that's where we have our minus 9.8 meters per second squared. So notice our minus signs are going to go away, and so we're going to be left with our twice 2.55. That gets us back to where we were, because it's vi sine 30 degrees. Notice our units are going to leave us with just seconds, which is what we want for time. So I got 5.109, 5.109 divided by 9.8. I got 0.5213 seconds is time. Now think about when people were rolling, having the Hot Wheels cars go off the edge of the table, you're getting about 0.4 seconds to fall that height of 1 meter. So this is also going to be a very short trip. We're launching a projectile at an angle, a fraction of a second, half a second. This is a reasonable amount of time. Oh boy, okay, so let's go back to our picture. Let's see what we've figured out. We figured out that the total time for the entire flight is 0.5213 seconds. Okay, that's for the whole trip. That's our time. We also found out what our velocity in the x direction is. Remember, that's over here. We got that by knowing the orange initial velocity and the angle, and knowing that the x component of that launch velocity in orange, the x component, x portion of it, is vi cosine theta. So we found velocity in the x we found was 4.425 meters per second. So now we want to find our delta x. That's the thing we want to predict. So that's going to be velocity in the x multiplied by time. So you can see already we've got our two variables that we need right there. Velocity 4.425 times a time of 0.5213. And that means I get a delta x here. This velocity is going down there. That time I wrote is going in there. And so I've got 2.307. If I round it, 2.307. And this is in meters because I got meters per second times seconds. Oh my goodness. That's how far away our little action hero who's taken one for the team needs to be from the launcher, the projectile launcher, in order to be struck by it. So that's how we can figure it out. 2.307 meters. Okay, and we'll see if it works. As a brief recap, what needed to happen here? First, we got a sketch going on. Okay, I decided to launch this thing at a 30-degree angle, and I didn't know this launch velocity. That was one thing I needed to find out. So I did what you did in the lab this week, and I had it launch horizontally and was able to work backwards to figure out the launch velocity, 5.109 meters per second. Then I adjusted it back up to 30 degrees and said, okay, I'm going to launch it at this angle, and I know the launch velocity by doing it horizontally first was going to be 5.109 meters per second. Since we're launching at an angle, we have to break it up into these red horizontal and green vertical pieces, which we use the sine and cosine functions to do, because we draw this right-angled triangle and we know the hypotenuse, we know the angle, so we can get the other sides in red and green. We mentioned some other things we know about surface-to-surface type launches, including what this maximum height thing is, where that appears, right in the middle. We mentioned that it's a perfectly symmetrical parabola here if we're going from the same launch height to the same landing height. And because it's the same launch and landing height, we mentioned that this means delta y is 0. For any STS type launch, delta y is 0. We took this information and we put it, by performing the same process as our previous problems with projectiles, into a T-chart, 2-column chart with horizontal and vertical stuff to keep everything organized. Make sure you define the directions and are clear about them. I like to always put them right there so I can see, okay, I'm calling down negative so I won't forget. And in this case, because this was in reality, I'm trying to actually hit this thing in the real world, I'm using minus 9.8 meters per second squared instead of minus 10. In the problems, assessment questions, you can just use 10 for little g, plus or minus. The other listed things that we knew are put in there. And I had look very similar process to the horizontally launched projectile stuff. I used second kinematic equation here to show I'm looking for my delta x, my range. I could figure out what the velocity in the x direction was because I knew what initial velocity was from having done the horizontal launch. I knew my angle was 30 degrees, so I got my velocity in the x direction right there, 4.425 meters per second. And so the only thing to find now was the time. Is the only other thing I needed in order to solve for delta x. So, just like with horizontally launched projectiles, we came over to the vertical side. Use my second kinematic equation here. I'm careful to look back at my chart to see, do I know if anything is 0? For STS type projectiles, delta y is 0. So I put that 0 in, solved my equation here for t, leaving everything as variables so I don't get flipped up, messed up by putting in numbers yet. Solve my equation for t. This is the total time. If I say delta y is 0, that means it's gone the whole trip. That's the total time. I substitute my values in now that I got everything isolated, and I got a time that looks nice and reasonable, about 0.5 seconds. Take that time back, doot-to-doot, into our horizontal stuff, just like we did with horizontally launched projectiles, and we got a value for our range about 307 meters.